everyone. Now we can start our new topic, which is very important, is the Terzaghi's one-dimensional consolidation theory. As you people know, Terzaghi sir is the father of geotechnical engineering, has suggested one theory for primary consolidation. Okay, we people understand what is the meaning of primary consolidation. We people have seen about the idea of primary consolidation, basic idea of secondary consolidation, and the compressibility that we have discussed in the previous lectures. Now people should see how to perform this study in laboratory, and who suggested this study, and what results we can get, that we can discuss in this lecture. So the Terzaghi's one-dimensional consolidation theory is given only for primary consolidation. It has not been given for secondary consolidation. Okay, so number of assumptions Terzaghi sir has taken. So those assumptions I have written here. One by one I will be explaining each and every assumption, and then we can start our calculation. Okay, so here see, first let me explain the experimental setup. What is the experimental setup? I want to tell you, we have one ring. Ring means we have one mold. That mold is open from top, that mold is open from bottom. That means I can say I have one hollow cylinder, this much height, not big, this much height. So I have one small mold like a hollow ring, hollow cylinder, which is open from the top, open from the bottom. Clear? One thing. Second thing, what we are going to discuss here, what we do, suppose this is that hollow ring. In this hollow ring, this is the hollow ring, it is open from top and bottom. We keep one porous plate on the top and one porous plate on the bottom. Now you people should ask me, what is porous plate? So porous plate is one plate made of stone which is having number of voids, right? So here we can have number of voids, number of pores in the plate. So the plate is called porous plate. Okay, so this plate is called porous plate. Now what happens here, we have filled this soil in the hollow ring, we have filled this soil, and from the top we kept one porous plate, bottom we kept one porous plate. Here what happens, if we keep the porous plate from top and bottom, and the soil which is filled in this mold is completely saturated, all the voids are filled with water, so the soil is completely saturated. Soil is completely saturated. In this condition, what we people do, we people allow the loading, we people allow the or apply the loading on this system. See, here also we have soil, here also we have soil, same soil. On the top we have one porous plate. If you want, I can write, this is the porous plate. Porous plate, all the voids means porous plate is a stone plate and it is having number of pores. Okay, here also if you want, I can write porous plate, or I can write porous plate here. Okay, if I am writing porous plate, it indicates actual situation of the ground. See, this is your clay soil. I have already discussed this study shall be done for clay soil only, because if I compare clay and sand, then the sand is having high permeability. Consolidation should not be studied in sand, it should be studied actually in the case of clay, because the water is draining out in the case of clay, taking a lot of time and showing a lot of settlement in the soil. So the study shall be done in the case of clay. So here in the mold I have filled the clay soil, and on the top and the bottom we kept the sandy soil in the ground actually. So in the lab, in the place of sandy soil, we can place the porous plate. Okay, So what is happening here, if you want, in the case of porous plate or in the place of porous plate, I can write permeable layer of sand, permeable layer of sand. This also, if you want, you can write. Okay. So in the ground there may be sandy soil which will be acting as a permeable layer for the clay. Okay. Or in the lab we can put the, or we can keep the porous plate. Now you see here this mold is filled with clay, the clay is fully saturated, we apply the force, something like this. So when we apply the force, what will happen? Excess pore water pressure will develop, right? So when the excess pore water pressure will develop, the water will try to drain out. So water is draining out in such situation. The half portion of water will go in upward direction, remaining half portion will go in downward direction. So you can see this is the direction of flow, something like this. Something like this, the half portion of water is draining out in upward direction and the remaining half portion of water is draining out in downward direction. You can observe. So one thing we people should notice, the water is flowing in one direction only. One direction means vertical. The water is flowing only in one direction, that is vertical. It can be flowing upward or vertically downward. Okay, it can flow vertically upward or vertically downward, but direction is one only, that is vertical. So from here we can say this is your two-way drainage. This system is called two-way drainage. Two-way drainage. Okay, this is the two-way drainage, and in this two-way drainage, why we people have given the name two-way? Because there are two ways. One way in upward direction water is flowing, second way in downward direction water is flowing. It is two-way drainage, but one directional flow. Direction is one only, that is vertical. Water is not flowing in x direction or in z direction. Water is flowing only in y direction, maybe in positive y, maybe in negative y, or both together. So when the water is flowing in one direction, then it can be one way, it can be two way. This is the example of two way. Half portion is going there, half portion is going there. This is called two-way drainage. Let's talk about one-way drainage. Let's see what happens here. If I talk about one-way drainage, this is the ring. Ring means your specimen, and then again the specimen is filled with saturated clay soil, for which we have to study the consolidation. Okay, something like this. Something like this. Here we kept one porous plate which is acting as a layer of sand, and here it is filled with water. Here we have not kept the porous plate at the bottom. Then what will happen? If you do not keep the porous plate at the water, if you do not place the porous plate at the bottom, the water will not flow in the downward direction. All the water will reach at the upward direction, because water has to drain out. So water is draining out only in vertical direction. So the water molecules which are present here, they will cover this distance and they are reaching at near the porous plate, and then they are draining out, something like this. So here one thing people should notice, again the direction of flow is one, single direction. That's why the theory name is one directional flow. That means theory name is one directional flow or one dimensional flow, that is vertical. But it can be one way or two way. So here this is the example of two way. This is the example of one way drainage. This is the example of one way drainage because the complete water is reaching and then it is draining out. Because the porous plate we kept at the top only. For example, if we keep the porous plate at the bottom, then the complete water will drain out in bottom. If we are keeping both side, then it shall be called, both side means top and bottom, then it shall be called two-way drainage. So here what is happening, if I talk about two-way drainage, direction of flow is one only, that is vertical, that's why the theory name is one dimensional flow, but the flow can be one way or two way. If I am telling the flow is two way, that means we are 100% sure the porous plate has been kept above the soil layer and below the soil layer. This is in the laboratory. The same role will be played by sandy layer in the ground. There can be a layer of sand, then layer of clay, then again layer of sand. It is the example of two-way drainage. Layer of sand, then layer of clay, then layer of sand. Example of two-way drainage. If at the ground we have layer of sand, then layer of clay, and then suppose rock surface start. So water cannot be drained out in downward direction because rock is present. Water has to flow in upward direction and through the porous plate. See, in the porous plate number of voids are there, number of pores are there. So easily water can be drained out through the porous plate. That's why we keep the porous plate. If we do not keep the porous plate, water will not be draining out. If there is no sand layer at the ground, the water cannot be draining out. So if we want consolidation to happen in the clay soil, then 101% sure we have to make sure that we have kept the porous plate, either top or top and bottom both. If we are keeping only at the top, one-way drainage. We are keeping on both the side, top and bottom, it is an example of two-way drainage. Let me talk about two-way drainage now. Suppose this is here, this is the complete initial height H0. So H0 is the thickness of compressible layer which is going to be compressed, or let me consider it is the initial thickness of clay layer. Okay, so if you want I can write H0 is the initial thickness of compressible layer. Compressible layer means clay layer. Clay layer. Okay. Here actually we want to find the D, and D is the drainage path. Now what is drainage path? What is the length of drainage path? Drainage path means the length of water covered in the soil. So how much distance water has covered in the soil? You can observe water started journey from here to here. This much distance water has covered, or this much distance from here to here water has covered. Means this is your D, drainage path, or I can say this is your D, drainage path. These two are the drainage path. Clear? So can you tell me what is the value of drainage path from here? Of course H0 by 2. So here in the case of two-way drainage, D will be equal to H0 by 2, right? If you are thinking like this, then it is wrong. Why, sir? Because one thing people should notice, we are going to apply the force, we are going to apply the load. So during this load, the volume of soil will reduce, means the volume of height will reduce. I mean to say the height of soil will reduce. So let me assume the settlement is delta H. If settlement is delta H, then this will not be the drainage path. Assuming delta H is the settlement of soil, compression of the soil also I can write, settlement of soil. If it is the settlement of soil, what is the net height available? Net height available is H0 minus delta H. This is the available height because delta H is the settlement. H0 minus delta H is the available height. Now it is divided by 2 to get the drainage path. So if you want, I can write the drainage path D can be written as H0 minus delta H divided by 2. One thing people should have noticed here, that is delta H is very less as compared to H0. So delta H can be ignored. So we are going to ignore the delta H. So I can write delta H can be ignored. So if the delta H is ignored, then the value of drainage path I can write D is equal to delta H we are ignoring. So finally H0 divided by 2, this is the drainage path. Initial thickness of soil sample divided by 2 will be the value of your drainage path. Clear? Okay. Now we can have the next discussion for one-way drainage. In the case of one-way drainage, we have sand layer, then compressible layer, that is clay layer. Compressible layer means the soil in which we are going to study the consolidation. I will be calling that compressible layer. It has high compressibility because it shows large settlement and taking lot of time to complete the primary consolidation. That's why sand shall not be called compressible layer, clay should be called compressible layer. So H0 is the thickness of compressible layer. So can you tell me what is the drainage path here? Of course, this will be your drainage path. Drainage path means the distance of water covered in this soil. How much distance water has covered in the soil, that is drainage path. So water has covered from here to here, it is called drainage path. So what can be the value of drainage path? Drainage path D will be equal to, what I can write? Drainage path I can write will be equal to H0. Am I right? No, you are not right. Why? Because here again the delta H will come in the picture because the load is applied, water is draining out, settlement of soil will occur, and this is the settlement of soil, so that we should subtract. But again the same study I will do, and I will write, since your delta H is very small or is less than H0, so this can be ignored. So I can write delta H can be ignored. If we are ignoring the delta H, final value of D we can have equal to H0. So this is the drainage path in the case of one-way drainage. So here till now what we have discussed about the experimental setup. Experimental setup, we are having, suppose we are going to perform the consolidation test, we should have one hollow cylinder of this much height, which is not actually cylinder, which is called ring, consolidometer. Okay, now fixed ring also sometimes it is called. Now what we are going to do, this ring is filled with saturated clay soil in which consolidation is performed. Now if you want one-way drainage, keep the porous plate only at the top. If you want two-way drainage, keep the porous plate on top and bottom. So when, sir, now you people should ask me, sir, when I should select the one-way drainage option and when should I select the two-way drainage option. So I suggest, if it depends upon your situation of the ground, situation of your soil. If at your location we have one layer of sand, one layer of clay, you should go with the one-way drainage. If in your if at your site your clay layer, your compressible layer is sandwiched between two layers of sand, means you have clay layer at your side, above the clay layer you have sand, below the clay layer you have sand, that means you should go with the two-way drainage. Okay. In the place of sand, sometimes you may have the what I can say, silty soil also, sandy silty soil also, you can have a silty sandy soil, you can have, no problem. Okay, so like that we can study one-way drainage and two-way drainage, and accordingly we can go with the test. Now after filling the rings with the soil, we keep the porous plate according to one-way and two-way drainage. Now we apply the load. One thing people should notice, that our soil which has been filled in the porous plate should be which has been filled in the ring should be fully saturated. Why the soil should be fully saturated? Because we are going to study the primary consolidation, and already we have discussed about the primary consolidation. Primary consolidation occurs after the compaction, and in the compaction the complete air has been removed. That means there is no air in the soil, all the voids are filled with water, so soil should be fully saturated. So here the soil which is filled in the mold will be fully saturated. Now this soil should have some properties, means in the form of assumption I can discuss. This soil should be homogeneous, isotropic and semi-infinite. What is the meaning of homogeneous? I think in the strength of material you people have already studied the meaning of homogeneity. Then also we can discuss. For example, I say the material is homogeneous. So mumaterial is homogeneous means, suppose this is the one material, and suppose if I am telling the material is homogeneous, that means, let me explain properly. If I am telling I have one material, this material, and this material is homogeneous, I can write this material is homogeneous. What is the meaning? The meaning is if I if I consider any direction in this material, then at each and every point in the given direction the property of material is same. Let me explain. If I say this is your x direction, so you select any point in the material, in this x direction property will be same. Suppose if I select this point, so in this direction suppose the property is E. Then if I select suppose this point, then in this direction the property will be E only. So suppose now I select this point, here also the property will be same E. If I select this point in this direction also, the property will be same E. Means at each and every point the property of the material in the given direction will be same. Now suppose if I say I have y direction somewhere here, something like this. So in the y direction, suppose we have property G. Then at this point also in the vertical direction we have the property G. In this vertical direction we will be having the property G. In the vertical direction we will be having the property G. So in the given direction, again at each and every point the property of the material is same. Now if I talk about the z direction, suppose this is my z direction. So in the given direction the property of material is same in each and every point or at each and every point. So here also I can say this one is here, suppose K. In the direction of Z we have K property. So here also we will be having K property, here also we will be having K property, here also we will be having K property. So at each and every point we have the same property in a given direction. Such materials are called homogeneous material. Okay, homogeneous material. Now next term comes isotropic. Your soil should be homogeneous as well as your soil should be isotropic. What is the meaning of isotropic material? So see, if I am telling one material is isotropic, that means This is your example of isotropic material. I can write here, this is your isotropic material. How it is isotropic? You see here what happens. You select any point. Suppose this is your x direction, this is your y direction, and this one is suppose your z direction. In the isotropic material, you select any point. Suppose I select this point. So in all the direction, property of the material is same. So if I am telling this in x direction we have E property, then in y direction also we have E property, and in z direction also we have E property. So at a given point, the property of material in all the direction is same, but we are not sure for this point. In this point, the property of the material in horizontal, it can be different from this point. Suppose in this direction it is G, in this direction it is G, and again in this direction G. So here we are bothered about the point. At any point, you select any point, in all the direction property of material is same, but it can be different from other point. At this point, again in all the direction property of material is same. If I select any other point, something like this, so here if it is K, then it can be K, it can be K. So in all the direction material property is same. Means here in the given direction material property is same at each and every point, and here at the given point the material property is same in all the direction. So basic difference should be cleared between homogeneous and isotropic material. Now if I am telling I have one material which is homogeneous and isotropic, it is homogeneous as well as isotropic. This is suppose your x direction, this is suppose your y direction, and this one is suppose your z direction, and I confirm this is your isotropic and homogeneous. Isotropic and homogeneous. Okay. If your material is isotropic as well as homogeneous, then you select any point. Suppose if I select this point in the given direction, suppose the property is E, then in this direction the property will be E, in this direction property will be E. Okay, this shows the isotropic material. Now if I select this point, in this direction also the property is E, in this direction the property is E, in this direction property is E. So it is satisfying. So next point, one more point. Suppose if I take somewhere here, suppose if I am taking, this is your again E, this will your E, and this is again your E. So what I observe, in the given direction X, at each and every point property is same. This is called homogeneous material. Now you select any point in all the direction property is same, it is called isotropic material. Means this material is isotropic as well as homogeneous, means you select any point in any direction, everywhere you will get the same property. This is called isotropic and homogeneous material, or homogeneous and isotropic material. Such material should be used, should be analyzed here in consolidation test. Okay, so I confirm we have used this soil for the study purpose. Clear? One thing. Second thing, you see here number of assumptions I have written here. The assumption number first, the soil is homogeneous, isotropic and semi-infinite. I have explained the meaning of homogeneous and isotropic. Let me explain the meaning of semi-infinite. What is semi-infinite? See, what is the meaning of infinite? Infinite means the system having the dimension in all the directions, okay, or changes will be in infinite directions. What is the meaning? Let me explain. Suppose if I am telling you if I am telling you this is my soil sample, okay, if I applied the load, now what will be the shape? The shape will be something like this. Am I right? If you compress this, lateral direction will expand. The material will expand in lateral direction, but it will get compressed in longitudinal, this direction, along the direction of load. So you are applying this system and getting this system. But we are not interested in this condition. What we want system to look like this. If the width is 5 centimeter, if the width of original sample is 5 centimeter, then here the width should be 5 centimeter only. Width should be 5 centimeter only. This is again same 5 centimeter. Load we are applying, but we are getting the changes. This is the settlement. This is the settlement. We are getting the changes only in the direction of depth. Means here in this condition, your soil was infinite, showing the changes in all the direction. In the direction of depth also, and in the direction of this lateral directions also. But here we have suggested to have semi-infinite material. Semi-infinite. Semi-infinite means changes will be observed only in the direction of depth. In this direction only the settlement shall be observed, the deformation shall be noticed. In this direction we do not want any change. So if you do not want any change in this lateral direction, then we should keep some lateral restraints, so that when I apply the force, the material should not expand in lateral direction. So therefore we have used lateral restraints. Lateral restraints we have used. How will you use lateral restraints, sir? Array, your specimen is itself a lateral restraint. We have used ring. We have used one hollow ring, and in this ring we kept the soil. So when you compress, changes will be observed in direction of depth. In this direction soil cannot expand because soil has been kept in the ring, and the ring is made of iron, steel. So soil cannot expand in lateral direction. So it is laterally what? Restrained. So such conditions are called semi-infinite. So your soil should be semi-infinite. Why? What is the reason why we people are doing like that? Because when I construct the footing, because of footing load is applied in vertical direction, and the soil present below the base of footing gets compressed. So this depth direction is finite for me, but this lateral direction is infinite for me. I have restrictions in the direction of depth, maybe up to 2 meter, 3 meter, 4 meter or 5 meter. Means we are doing the finite study, okay, in the direction of depth, but the area is infinite of the soil. The lateral directions are infinite. That's why in the laboratory you people should notice, you purchase one plot, you prepare your building, how much excavation will you do? 2 meter, 3 meter, 4 meter, 5 meter, bus, sufficient? Means we have finite study in the direction of depth. Not talk about area. Area is infinite. This side also positive x, this side also negative x. How will you measure this settlement or this deformation? We can't measure, because in the lateral direction soil is infinite. In this direction, in the direction of depth, it is finite. We can measure the settlement using the what we say, dial gauge. But in lateral direction, how will you measure in the ground? It is infinite. That's why I have to create here the semi-infinite condition. Means your soil sample should be finite in one direction and semi-infinite in another direction. So your soil sample should be finite in the direction of depth, and your soil sample should be infinite in the direction of area. It's a lateral direction, lateral dimension, maybe x, maybe z, but in the direction of y it is finite. So that's why we have used a ring as a specimen which is made of steel, hard, stiff. You apply the force, steel will not expand, soil will not expand, only soil will get reduced because there are number of voids in the soil, so soil volume will reduce in the vertical direction. So when the volume of soil will reduce in vertical direction, something like this. So if you assume I am applying the load, so water will coming out, draining out. So water cannot drain out in this direction. If this is the soil sample, we have kept a drainage system here, we have kept one drainage system here. Water cannot flow in lateral direction, something like this. Water cannot flow. Water cannot flow in lateral direction. Water will flow only in vertical direction, something like this. Maybe in one way, maybe in two way. So this lateral movement of water is not allowed and it is not possible. Why? Because we have used ring, steel ring. How water will flow out of the ring? It is not possible. Water will flow in one direction only. That's why the theory name is one-dimensional consolidation theory. This one direction flow may be one way or two way, that I have already explained. So here I have mentioned so many assumptions. Soil is homogeneous, isotropic and semi-infinite. We have discussed about it. The soil is fully saturated throughout the test. Already we have discussed about it. The soil is restrained against the lateral deformation. We have discussed we do not want lateral deformation because the soil is semi-infinite. The soil is semi-infinite. So to make the soil semi-infinite, we have laterally restrained our soil sample. Okay. That means water is allowed to move only in vertical direction. We have discussed. The flow of water is one dimensional, that is vertical. That means flow of water should be in direction of depth. In the direction of depth means in vertical direction water will flow. That means changes of volume shall be observed in the direction of depth. Whatever changes will be observed shall be observed in the direction of depth, not in the direction of lateral dimensions. Okay. So this also we have discussed. The flow can be one way or two way, that we have discussed. The flow of water is laminar and Darcy's law is valid. Okay. So the flow of water which is happening may be in one way or two way. It should be in laminar conditions. I think you people have studied about the laminar flow because I have explained in the chapter number 2 about the laminar flow. Zone number 1, it occurs in the case of some special kind of soils, and when there is a laminar flow, we can apply the Darcy's law. V is directly proportional to I. So if we want to remove the proportionality sign, we can use the hydraulic conductivity, that is V is equal to Ki, right? So Darcy's law can be used here. Load is applied in one direction. So here the load we will not apply it like this. We will not apply like this also. We cannot apply like this. We cannot apply like this. Means from lateral direction we do not apply the load. We apply only from the vertical direction because we are studying the one-dimensional consolidation. So from vertical direction only the load is applied. So because from the lateral direction soil is confined or restrained, I can say, the plastic readjustment of the soil solids can be ignored. Means we are ignoring the secondary settlement. Terzaghi sir has ignored the secondary settlement. He has given the theory only for primary consolidation. And actually we are interested in primary consolidation. Why? Because what happens, the secondary consolidation occurs after the primary consolidation, and the primary consolidation is completed in infinite time. It takes infinite time. So when the secondary consolidation occurs after infinite time, it has less significance. It has less significance because after infinite time it is occurring. First the primary consolidation let completed. So if I talk about secondary consolidation, it has less significance as compared to primary consolidation, because first the primary consolidation will occur in infinite time, then secondary consolidation will occur. So here actually primary consolidation occurs after infinite time, but for all practical analysis, for practical aspects, we can assume primary consolidation to complete at 90% degree of consolidation. We'll discuss, don't worry. So till now I have explained what is one-way drainage, what is two-way drainage, how the experimental setup of primary consolidation is prepared, and what are the assumptions given by Terzaghi analysis, given by Terzaghi sir. All those things we have discussed till now. Now what results actually we get in this test, that we can discuss. Now let me take, suppose this system, suppose we are performing two-way drainage in our laboratory. So this system, let me take, I am taking this system and I am plotting this system here. So you can observe I am going to plot the same system again here, something like this. Okay, something like this. Here we have one porous plate, here we can have one porous plate. One thing I want to clear you, all the voids of the soil is fully saturated. Fully saturated. So what will happen? If voids are fully saturated, they can be having the pore pressure. You understand? This is the example of your two-way drainage. Two-way drainage. Suppose I have prepared the experimental setup. Till now I have not applied the load. In the last class, you people have studied about the primary consolidation, if you remember. In the primary consolidation, what happens? We have one ground, something like this, which is fully saturated. Okay. Total stress is suppose 50, so suppose it is 100. Pore pressure is suppose 50 or suppose 30. So effective stress, what is the value? 70. Total stress minus pore water pressure is clear. So what I am going to suggest, you have total stress, you have pore water pressure, you have effective stress. So if you do not construct any building on the ground, then also this effective stress, total stress and pore water pressure is present because of the self-weight of the soil. Clear? So because of self-weight of the soil, these three stresses are already present. So that this is the condition of the ground. Till now I have not prepared the structure. Assume there is a sand layer in your ground. Assume there is a sand layer in your ground, and here we have clay layer in your ground. If I insert one piezometer somewhere here, if I insert one piezometer somewhere here, then what will happen? It will rise. Water will rise in the piezometer up to this level. Up to this level, suppose. Now suppose if I apply the piezometer, I insert the piezometer somewhere here, again the water will rise up to this height like this, and pore water pressure can be measured. Now if I insert the piezometer something like this, somewhere here, we are inserting the piezometers. So this is the rise in the water in the piezometer tube. So the in the piezometer, like that we can get the rise of water. Okay. One thing people should notice, all the level of water are at the same level. Clear? So this is the condition when, when okay, wait, 1 minute. Water table is not rising here, water table is actually somewhere here. Let me assume that is also correct, but here the space is not there, so I am drawing. Let me assume the water table is somewhere here. Water table is somewhere here. This is your water table. In this tube, here we have water table, here we have water table. So of course this is the same condition. If I insert the piezometer here, water table is located here, so water will not rise, you will get the water table here only, rising tube. If I insert the piezometer somewhere here, water will rise up to the same level here. If I insert the piezometer somewhere here, again the water table will rise up to here. Means if I measure on the top surface, if I measure on the bottom surface or at any middle portion, the water table will be at the same level because water is not flowing. If the water is not flowing, there will be no head loss. If there is no head loss, everywhere the water table is at the same level. The head is at the same level. The pressure head is constant everywhere throughout the depth of soil. So here also everywhere we are getting the same rise. At this level we have water table. Now what is going to happen? I am going to construct one building on this soil. I have constructed one building. As I construct the building, maybe of additional load delta sigma or additional pressure delta sigma equal to 50. The complete value of 50 will be taken by, you see, in the last class we have discussed about the primary consolidation. At T equal to 0, total stress, this is delta sigma, will be completely taken by pore water pressure delta U. Clear? So that time, what is the value of effective stress? Delta sigma bar 0. This is the condition at T equal to 0. At T equal to 0. So immediately the complete value of delta sigma will be taken by pore water pressure. Means this 50 additionally we have applied. Complete value of 50 is taken by water. Soil solids at the time will not take any value. If soil solid is not taking any value, suddenly what will happen? This is the condition when no pressure, no delta sigma bar has been applied. I think it is clear to you. At this level, this is our initial level. Okay. Now what will happen? As you prepare the structure here also you have applied the pressure of, let me tell you, of value delta sigma. Okay. As you apply the pressure of delta sigma here, the complete delta sigma will be taken by pore water pressure. So as it is taken by pore water pressure, so this pore water pressure will rise because the value of pore water pressure is increasing. Now 30 plus 50, this is the additional value. So from here it will shift to here, additional value. From here to it will shift there, additional value. From here to here, additional value. What is the magnitude or from here to here? this is equal to additional value 50 delta U, and this delta U is equal to delta sigma at T equal to 0 immediately. So this picture I have created at T equal to 0 when your additional pore water pressure, which is known as excess pore water pressure, becomes equal to additional applied total stress. Is the applied total stress. Now as the time passes, what happened? Your total stress is continued, but pore water pressure starts reducing, it starts dissipating from the top and from the bottom. If it is two-way drainage, first water will be removed from the top and from the bottom. So here the pore water pressure will be something like this. Means you should notice I have inserted the piezometer at the top, I have inserted the piezometer at the bottom. So first the water will remove from, first the water which is present near the top surface and near the bottom surface will be drained out. The maximum water, the maximum time will be taken by the water which is present near the mid portion, because it has to cover either this distance or this distance. So it takes a lot of time. If it takes a lot of time, means here we have high pore water pressure, here pore water pressure is 0, here pore water pressure is 0. So if I talk about the time T which is greater than 0 but less than infinite, what will happen? If I insert the piezometer in the middle portion, it will rise up to somewhere here. Up to somewhere here. Means your water initially was here at T equal to 0, now it has been dropped somewhere here. Okay, it has been dropped. But if I insert the piezometer here, we are getting the water table here only, because from here excess pore water pressure is dissipated. If I insert the piezometer here, from here also excess pore water pressure is dissipated. So here also you are getting at the same level, old one, when the value was not applied. So this excess pore water pressure is started dissipating, and excess pore water pressure becomes 0 at the top and at the bottom. You can see 0 and 0. So here again you are getting the same value, here also you are getting the same value. So if you want, I can connect something like this. Now after infinite time, if I talk about T greater than or equal to infinite, total stress is also present. Total stress is still present, but the pore water pressure will become 0. Excess pore water pressure will become 0. When the excess pore water pressure will become 0, if I insert the piezometer anywhere, it will rise. If I insert the piezometer here, it will rise up to here. If I insert the piezometer, it will rise up to here. It will rise, it will here. So this picture, this one I have created at T greater than 0 but less than infinite, and this I have created at T greater than or equal to infinite. Clear? So at this condition, after infinite time, your entire value of excess pore water pressure will become 0. So the final value of pore water pressure U will become again equal to 30. This 30. This excess value is becoming 0 after infinite time. The complete excess pore water pressure is removed. So U will become again equal to 30 only. So you can see again it has reached to the initial values of pore water pressure. Are you getting my point? This line we have started, this is the initial line of pore pressures, initial line when there was no building. We have constructed one building, pore water pressure increased up to here because the complete weight of structure has been taken by water. So pore water pressure is increased up to here. Now as the time passes, pore water pressure starts decreasing. So pore pressure starts decreasing. Near the top surface and near the bottom surface, first the excess pore water pressure will become 0, at the top surface and the bottom surface. So here it is becoming 0, here it is becoming 0, and the middle portion takes some time. After infinite time, the excess pore water pressure will completely become 0. Again we have reached to initial condition. Means whatever excess amount of pore water pressure was coming, that is completely dissipated after infinite time. So this is the complete picture. This line is connecting the water tables, not water tables exactly, the rise in waters. So this is called piezometric surface, this is called piezometric surface, this is called piezometric surface. It is also called isochrons. The points which connects, or I can say the contour which connects the points of equal pressure head is called isochron. So I can say this is your isochron. If you want, I can write this line, this curve, this horizontal line, all are called isochron. For 1 mark it can be asked. Isochrons. Okay. So this is the complete picture of your theory. This is the experimental setup and these results we should get. So for explanation, I have written and prepared those 9 figures again here. One thing people should notice, the water was draining out somewhere here, and the water was draining out, remaining water of half portion is draining out somewhere here. Okay. So like that, it is the example of two-way drainage, and we are getting this 9 figures here also. This is related to first 3 figures, this is related to second line 3 figures, and this is remaining 3 figures. So 3, 3, 3, total 9 figures. Clear? So this is the example, or this is the study of primary consolidation. So till now we have discussed about the one-way drainage, two-way drainage. We have discussed about the different assumptions, explanation of each and every assumption, and we have seen the experimental setup. We have seen what is homogeneous soil, isotropic soil, homogeneous and isotropic soil, and how the isochrons are obtained in the lab, how the actual pore water pressure distribution occurs, that also we have seen, how the actual primary consolidation occurs in the lab, that also we have seen. So till now I have discussed the entire theory portion of the Terzaghi's one-dimensional consolidation theory. Clear? Now we have to see, we should talk about the results. What results we are getting here, that we have to discuss. Okay.